Hello, in this video we're gonna do a quick review of Castigliano's theorem to find the deflection at point C. One rule to remember is that in order to use Castigliano's theorem, there must be a concentrated load at the point of interest and the deflection must go in the direction of that load. So looking at our problem, we don't see a concentrated load at our point of interest, which is point C. So we're going to apply a dummy load at point C, like this, and call it P. Now, we're going to draw the free body diagram of our beam and find the reactions in terms of the dummy load we applied, P. So By, Ay, and then we have 60. Let me write that better. So 60 kips acting on the center of the distributed load, so 15 feet from point A. So the distance is 15 feet. Okay, well now we can do the sum of forces in the y direction. It's gonna be equal to Ay minus 60 plus By minus P, which is equal to 0, and the moment at point A, assuming rotation to be positive counterclockwise. So if we take the moment at point A, it's going to be negative 60 times 15 plus By times 30 so 30 right here minus P times 40. It's going to be equal to 0. So now you can find By in terms of P. And if you do the calculation, By will turn out to be 30 plus 4P over 3. That's your reaction at the roller B. And if you plug in By into this formula, you're gonna find the reaction Ay, which comes out to be 30 minus P over 3. So now once we found our reactions, we're gonna do section cuts in our beam, 2 section cuts to be exact. So section cut here, let's call this section cut AB, and the section cut right there, and let's call this BC. And now we're gonna draw the free body diagram for each section cut. So let's do that really quick right here. So section cut AB, we're gonna have a reaction Ay, which is equal to 30 minus P over 3, and we're gonna have a moment. Let's call this M1. And X is gonna go in this direction. And remember, we had 2 kips per feet, so we're gonna multiply 2 since our distance is x now, it's going to be 2x. And we're going to do the same thing. Our equilibrium equation, assuming positive rotation in the counterclockwise direction, and it's going to be m1 plus 2x over times x over 2, because it's acting on the centroid, minus 30 minus p over 3x. So, and this should be equal to 0, so if you solve for m1, it's gonna come out to be 30 minus p over 3x minus x squared. So here's your m1. Now let's do second section cut, which is, if we go back, it's BC. So let's do BC, and it's gonna be the same thing, except for BC, you can stand right here and look that direction, and you're gonna see the distributed load, or you can look in this direction and you're gonna see only the concentrated load P, which is our dummy load. So it's easier to look in this direction instead of looking that way. I mean, both are correct, but I mean, it's easier to look in this direction. So let's do that. Let's draw our free body diagram. Section cut. Here's our dummy load P, and here's our moment. Let's call this M2, and now this is point C right here, and now we're gonna have distance x prime. Okay, let's do our equilibrium equations. Same thing, positive rotation in the counterclockwise direction. So it's gonna be negative m2 minus px, which is equal to 0. So m2 is gonna be equal to negative px. Okay, now once we found our moments, oh, one thing to remember, we did not include the shear force right at the section cut. No shear force, because the problem stated that it's a cylinder beam, so you can neglect the shear force. So here's our M1, here's our M2. Let's look at the general formula for Castigliano's theorem. So I'm gonna have it right here. Here's the general formula for Castigliano's theorem. So you have 4 terms. First term, second term, third, fourth. This term is due to axial loading. This one is due to bending. This one is due to torque. And this one is due to shear force. Remember, in our problem, there is no axial load, so this is 0. We do have bending, we found the moment. The torque is 0. And, I mean, the shear force is not 0, but we're neglecting it because it's a slender beam. So we can assume this to be 0. So let's do a small table with the 2 different segments. So segment origin limits moment and dm over dp, the partial derivative of the moment with respect to the load P. So segment AB, the origin was at point A, the limits, let's go back, so the origin is at point A, the limits is from 0 to 30, so let's go back, 0 to 30, moment, well, it's going to be M1, we found that to be this one, so let me extend this one, dm over dp, and m1 was 30 minus p over 3 times x, so 30 minus p over 3 times x minus x squared. dm over dp, it's gonna be minus x over 3. So for segment BC, let's go back to segment BC. So here's C, and here's B. And the origin, I mean, we looked that way, so the origin is from C to B. Let's go back. The origin is at point C, and it starts from 0 to 10 feet. And M2 came out to be negative px, so negative px, dm over dp, it's going to be negative x. Now since our table is ready, we can plug in the values into our formula for deflection. And remember, for each section cut you have to write the deflection formula. So we're going to have two bending terms, one bending term for section AB and the other one for BC. So let's write this. Deflection at point C, it's going to be equal to 1 over EI, the integral from 0 to 30, M1, which is 30 minus p over 3 x minus x squared times dm over dp, which is negative x over 3 dx. And this is for segment AB. For segment BC, same thing, 1 over EI from 0 to 10, negative x prime times negative px prime dx prime. Now remember, we applied the dummy load, so p is equal to 0. If you remember, p is equal to 0, it's just a dummy load. So let's go here. So this is gonna be equal to 0. This one, p right here, is gonna be equal to 0. So if we simplify this integral, we're gonna see 1 over Young's modulus, which is 29,000 ksi, and for the moment of inertia it's gonna be 2,000 n to the 4th. So 29,000 times 2,000, and it's going to be the integral from 0 to 30 x minus x squared times negative x over 3 dx, and this comes out to be, let me do it on my calculator really quick. So it's gonna come out to be negative 22500 over, this is kips feet cubed, and this is 29,000 times 2,000. And we're gonna have to do some unit conversion because this is in feet and these right here is in are in inches. So let's do that really quick. So negative 22500 times 12 cubed, convert it to inches, and then 29,000 times 2,000. And this is gonna be equal to negative 0.67 inches. Hope you find the video to be helpful. Thank you.